Hello and welcome to ACM's fifth learning webinar. This webinar reflects ACM's deep commitment to lifelong learning. Our aim is to empower computing professionals and students who join ACM's worldwide community of 100,000 plus members. My name is Yannis Ioannidis. I'm currently a professor at the Department of Informatics and Telecommunications of the University of Athens, as well as the President and General Director of the Athena Research and Innovation Center, both in Athens, Greece. I'm an ACM Fellow, and I'm currently serving as a 4-year term as Chair of ACM SIGMOD. I'll be serving as the moderator for today's webinar. ACM offers innovative educational and professional development resources that bolster skill sets and enhance career development opportunities. Our members are able to stay competitive in the dynamic computing world with a range of ACM Learning Center online resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. Together with timely computing information published by ACM, access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics, ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. I'm here representing the ACM Special Interest Group on the Management of Data, SIGMOD, which in addition to cooperating in this event is proud to publish the SIGMOD Record, its quarterly bulletin, and to sponsor a number of top conferences in the field, including the annual SIGMOD PODS Conference on the Management of Data, as well as the new and very relevant to today's presentation, Symposium on Cloud Computing, co-sponsored with ACM SIGOPS. Big data is really big these days, and ACM SIGMOD is its home. Today's presentation is Condos and Clouds, Patterns in SaaS Applications by Pat Helland, currently a software architect at salesforce.com. Some housekeeping items before we get started. At the end of our presentation, we will have time for questions, and we hope you have several. Also watch for live poll questions during the presentation. You can submit your answer now by clicking the Submit button when the time comes. In the top right corner of the slide area on your screen, there is a green button that will allow you to enlarge the slides. You may also enlarge the slides at any time by dragging the corner of the slide window. The slides will advance automatically throughout the event. You can minimize the slide area, Q&A, and bio screens using the buttons on the bottom panel. If you're experiencing problems with the program, please press the F5 key on your keyboard if you're using Windows, or Command+R if you're on a Mac, to refresh your console or close and relaunch the presentation. You can also visit the webcast help guide by clicking on the Help widget below the slide window. Please disable pop-up blocking software so you can receive and respond to the feedback form at the end of this presentation. To control volume, adjust the master volume on your computer. This session is being recorded and will be archived. It will be available for review in the next few days at learning.acm.org/webinar/condos. If you think of a question during the presentation, please type it into the Q&A box on the lower left of the presentation screen and click on the Submit button. You do not need to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box to suggest topics for future webinars of interest to you. And now I'd like to introduce our speaker. We are honored to have presenting today Pat Helland. Pat has been working in distributed systems, transaction processing, databases, and similar areas since 1978. For most of the 1980s, he was the chief architect of Tandem Computer's Transaction Monitoring Facility, or TMF, which provided distributed transactions for the non-stop system. Pat has worked at Microsoft since 1994, where he was the architect for Microsoft Transaction Server and SQL Service Broker. Until September 2011, he was working on Cosmos, a distributed computation and storage system that provides backend support for Bing. He has also spent 2 years at Amazon. Pat recently located to San Francisco and joined Salesforce.com to work on multi-tenanted data and various projects in cloud computing. Pat, we look forward to your presentation here today.
Thank you, Yannis. It's a great pleasure to be here. I'd like to talk about this talk, Condos and Clouds, which I wrote before going to Salesforce. I love being at Salesforce. I love cloud computing, and I love the technology here. But I want to make sure everyone understands I'm going to talk about an architecture for software as a service, and while it's very similar to Salesforce, it has some differences. And so don't expect that this is actually Salesforce's architecture. But let's get started. So I want to start with an outline. First of all, we're going to have an introduction. Then we're going to talk about patterns in software as a service applications and the front end. Then we're going to move on to the back end and decision support, having a section on multi-tenancy, making it work, and a conclusion. Let's do the introduction. So first of all, I live in a condo. And that actually is where I lived until I moved from Seattle down to San Francisco about a year ago. And that's a great condo. And, you know, I loved it. It had a great view. My ears popped on the way going home, and it was pretty darn cool. Not everyone wants to live in a condo. You know, I love it because my kids are grown and they've got grandkids, but it's not good if you've got kids playing in the backyard, dogs running in the backyard, you want to work on cabinetry or have a garden. But there's these amazing advantages to living in a condo. The heating and air conditioning just works. You have an infinite supply of hot water, so you don't have to worry about long showers. Somebody else takes trash out to the streets. And indeed, in 3 out of the 4 last homes I've lived in, I've had a trash chute. And a trash chute is just an amazingly fun thing because you can push stuff down it and it goes away and makes a heck of a racket. This condo also comes with a building engineer who fixes most of the things. And so the point I want to make is that sometimes it's really, really nice to outsource a bunch of hassles. But when you get to outsource those hassles, you actually do have to live with some constraints. So what are the constraints and the concierge services we see in various buildings? If you're in a housing environment, a condo building, somebody helps you with reservations and they pick up packages and dry cleaning for you. There's this exercise facility and a pool that you get to share, the engineering shared. But at the same time, parking has its constraints, noise has its constraints. There's restrictions on pets and barbecues, and you can't work on your car in the garage, and you can't have a garden. When you go to an office building and you have a shared office building, you have the advantage of shared bathrooms, a lobby, copiers, and coffee are sometimes shared engineering when things are broken. But the constraints typically are that you have a fixed office layout. You probably get told you're not allowed to sleep at work. You probably are told you can't have pets. In some environments, you even have a dress code, and you have to dress a certain way to go in and out of the building. And finally, if you think of a retail mall where you're sharing a space, again, the engineering, the parking, the common space, the security are all shared to your advantage. But you get told some rules. You have to have your store open the same hours as the mall. You have constraints on the kinds of retail activity you get to do. And there's probably constraints on, having it only be retail activities. So the question I want to drive is, what are the constraints and the concierge services in cloud computing? How can some infrastructure make your life better for sharing an application, and what constraints do you have to impose on that sharing application so it can fit into that shared cloud? So I have a question now. Do you have a trash chute? I'm waiting to see. Does anybody have a trash chute? Come on, we can vote. Wake up. Who has a trash chute? Nobody's answering me. I want to know if you have a trash chute. This is a poll. You have to click on the result, yes or no. I'm getting no answers on the trash chute. Okay, you guys are complete failures. You haven't helped me and participated by saying whether you have a trash chute. So the next question is, do you throw wine bottles down the chute without placing them in a bag to soften the racket? Can you answer this one? Please, I'd like to see, are there results for this? And the answer is no. Okay, so I'm going to say nobody pushes wine bottles. I'm telling you, pushing a wine bottle down a trash chute is a wonderful, fun thing to do. Okay, moving ahead. What is cloud computing? Cloud computing is applications delivered as services over the internet or intranet. So some terms we've seen, very popular terms, are software as a service, or SaaS. And that is, I get on the internet and I see an application coming to me over the internet. Now, utility computing is virtualized hardware and computing that's delivered over the net. So when you look at the box on the right, you see a cloud provider. So, Amazon.com is the one we all are aware of when they're doing the Amazon Web Services. And they provide utility computing. On top of that, you have someone who's using the utility computing and a software as a service provider that is then showing a web application out to the user. Now, there are 3 new aspects to cloud computing in the last few years that are really, really interesting. First, there's the illusion of infinite computing resources available on demand. Second, you don't have to have an upfront commitment, to be a user. You kind of sign up, you say, I'm going to use it, and then the more you use, the more you get charged. There's not typically a commitment to the amount of cloud computing that you're going to use. And so and third is the ability to pay for the use of those computing resources on a short-term basis. If you go to AWS, Amazon Web Services, you can get an hour's worth of 100 computers, and it doesn't cost you. You're surging in and out of that, and it's that total amount of usage that you pay for, and you can adjust it and adapt it very, very rapidly. So cloud computing allows deploying software as a service and scaling on demand without needing to build or provision a data center. Now, I want to point out this slide, and all of the stuff on this slide is directly copied from a wonderful paper that I strongly recommend called Above the Clouds, A Berkeley View of Cloud Computing, and it's got this and more in it, which is really a fun paper. So now, what are the forces that are driving us to the cloud? First, there's an issue of data center economics. So in utility computing, I can actually have many different people coming along and joining in and sharing the same resource, which gives me an efficiency of size. I can, with a big data center, I can put it where there's cheap networking, where electricity is cheap, I can do networking on a main line, I can even get containerized servers and share standardized admin. And that sharing reduces the cost of the computing very, very dramatically. A parallel that I find interesting, which I saw written up in the Above the Clouds paper, is this notion of a chip foundry. If you go back 10, 15, 20 years, the cost of manufacturing a chip and building a foundry that could manufacture a chip was getting to be so large that the major chip manufacturers couldn't pay for it with their own business, with their own chips that they needed to produce. So they started to say, I'm going to charge somebody to produce other chips that are not my leading business. So, for example, Intel continued to make its own foundry, but started letting other people manufacture chips for a fee using that building, and then they could amortize the building, allowing them to create a more efficient and deeper geometries and better chips by amortizing that cost. That's very similar to what we're seeing in cloud computing, where the cost of a data center can be so high, but the value is so high that we're needing to share them. The next force that's driving us to the cloud is shared data. If we have a common big data store that allows us to look at things and ask what-if questions that literally were not thought of at the time you were arranging to put the data into one big heap, right? So that value of surprising serendipitous discovery grows as the data size grows. And so we're seeing a trend where a typical enterprise wants to store all of their data in a common store. If they store the data and allow analysis, frequently they can see very surprising value. And so, this was something I noticed a lot in Bing. It was like, wow, push all this data together, and you see these interesting business values that come out. And all of the big companies are experiencing this. Shared resources. If I have computing resources and I can run them at a higher utilization, a higher statistical utilization, then that allows me to pay for them less expensively. So by sharing the usage of computation and storage, I can then let people use these computers and use this storage at a time when other people would back off and get more slack. Retailing, the act of buying things online, tends to have its annual peak before Christmas. But photo sharing tends to have its annual peak in January as people are sorting through the holiday pictures and sharing them. So that shared usage allows for the peaks to be spread around for different things. And a stronger SLA, meaning that you can give high priority work that preempts low priority work, and as long as you can make that work fluid and fungible, we can share very, very well. So the next piece that I want to talk about is, as you look at most of these software as a service applications, they're broken into two broad sections, the front end and the back end, with the back end also kind of overlapping and doing decision support. So the front end online processing is web service or HTML user facing, and it is very typical for an SLA to be under 500 milliseconds. Typically it's 200 to 300 milliseconds you're looking for, right? And that back end processing is doing stuff that can take longer. It's consuming crawled data from the web, or feeds you got from partners, or logging information. So that front end stuff is generating logs about who saw what and what they did with it, and then that gets crunched to analyze the data to figure out what are we going to do in a big batch job in the back end. So decision support gives us ad hoc and planned analysis of the data sets that are in the back end. And so there's this integrated processing where it's unclear distinction between the back end and the decision support all doing that. But what is clear in the pattern that you see is the back end stuff is crunching and presenting results which are then used for the front end to show to the people, which then typically creates stuff that you're pushing into the back end. So now let's go and focus in on the patterns that are in software as a service applications when focusing in on the front end. So many services fit a pattern. So what happens is a request comes in from the web and gets hooked up to a piece of computation that can process that request. You may then say, oh, I need to remember the state that I had the last time I talked to that specific user. So now you run off to a session state manager, get some session state, and now you're ready to continue. Oh, now the app may say, oh, I actually want to talk to some other services that are in my data center that are going to do some other pieces of computation for that. And then the app may access data from an application data cache that's populated from that back-end feed processing. And so now I'm looking at product catalog, I'm looking at price lists, I'm looking at things that I need, not just about what the user saw the last time, but what he's now looking at to do their work. And then with that, we will typically issue a response. Now the point I want to make here is that this is a consistent pattern. And if we follow this pattern, we can start building plumbing that lets the user not have to build as much and outsource many of the hassles. And I want to point out that's a lot like living in a condo with a building engineer. If you fit within the pattern, you can get a lot of cool services. So what are the services I'm going to posit we could build in such an environment? There's auto-scaling. Hey, the workload went up. I'm going to find some servers. I'm going to add it to it so I can, configure my system to dynamically handle more work as it comes. Auto-placement. If I do deployment, migration, fault boundaries, geographic transparency, all of this stuff. Managed for the application. Application doesn't give a darn. It's ignorant. It all works. capacity planning. So when you watch the traffic patterns, you watch how they change day to day, week to week, month to month, year to year, you can see trends of the user workload, which then say, maybe I better get some more computers, maybe I better get some more storage in order to make this stuff work. A resource marketplace. So what the idea there is, if one service calls another service, which calls another service, how much of that deeper services work was attributed to that specific top-end service? How do you look and track at the cost amortization of one service beating up on another one so that you can decide, hey, this is what it cost me to do this work? A/B testing and experimentation. Anybody who's lived in this web service world knows you don't go change things. You change it and send a little bit of the work into it, and then see how bad it is, how good it is. Did this improve my sales? Did it make it better? Did it make it worse? And then if you're trying something and people like it more, then you gradually roll it out. And this is typically called A/B testing and experimentation. There's no reason why you can't have plumbing help you with running two of these things side by side and shunting a percentage of the traffic into the new thing. Auto caching and data distribution. So I want to have a data store that the back end is running and figuring out new product catalogs, new price lists, new insurance quotes, all of the things I want to do, and then push it out to where the front end can access it efficiently. But managing the scale of the data and the scale of the traffic is something that the application itself should be able to look at the plumbing to do. It should be an automatically provided concierge services. And finally, session state management. The easiest one to think about is a shopping cart. Where the heck do you put the shopping cart? How do you find the shopping cart when the user comes back? How do you make that durable? How durable need it be as time goes on? All of this stuff can be built into the system and then available to the application so they don't have to worry so much about that. Now, stateless request processing. Incoming requests are routed to one of the copies of the service, and at first there's no state. At that point you consider it to be stateless. And the plumbing should keep a pool. The more traffic, the more you want to allocate into that pool to make sure that the performance and the SLAs can be kept up with. That's stateless request processing. Composite request processing. A service gets called and it may call other services, which call other services, which call other services, and the answers go out and they come back. And you see this is a very rich and deep cycle in many, many systems. And how do you manage that? Now, this brings us to the question of SLAs, or service level agreements. Does the service get the answer as fast and as often and as accurately as it's promised? Is that response fast enough? System-wide SLAs need very tight component SLAs. And so for an example, I may want a 300 millisecond response time for 99.9% of the requests, assuming a traffic rate of 500 requests a second. But I've got all these services crossing all of the others. And typically you want to measure a percentile response time because it's much tougher on the software engineering and provides a much better user experience. So if I have a deep call stack like this, and things are going calling to calling to calling to calling, you end up with a world where it's just pretty tough as you get farther down the stack. There's a lot of pressure on the bottom of that stack, and you need to answer that bottom of the stack very quickly, fast, and predictably. I'm pounding on those services at the bottom. The deeper the call stack, the tighter the SLA. So when I go back to that session state manager, which would keep shopping carts and things like that, or the auto cache manager, which would keep the product catalog, the price list, they get called a lot. They're very deep in the stack. The deeper the stack, the more the pressure. And that may result in sacrificing utilization. How are you going to provide that tight SLA? With a short minimum response time, a really low utilization, or both? If you remember from your queuing theory, the expected response time is a function of both the minimum response time and 1 minus the utilization. So a half-busy system, 50% utilized, is going to take twice as long as an empty system. A 90% utilized system is going to only have the slack of 10%, so it's going to take 10 times as long. And so the way we deal with that in this class of system is you actually create more images of the service so that their utilization drops, and with their utilization dropping, they can get the answer faster, and that can help you keep your service level agreements. All of this stuff is stuff that could be automatically provided. So automatic provisioning to meet SLAs. If the plumbing knows the desired SLA that the end user has and knows which services can call on which other ones, that desired SLA, to meet the desired SLA, you can calculate what you need for the deeper SLAs. So we have not, as an industry, gotten to the point of automating this, but it is something that we can and should aspire to, tracking all of this and managing automatically, increasing the provisioning for the stuff when it gets under SLA limits. And so you could, within limits, the SLA can be met by increasing the number of servers. And this technique is useful for many, many things, but not everything. The reason I say that is because the absolute minimum response time, the time that you get an answer back on an empty system, still has to be within limits. So it can't completely cover everything. So what is one technique to reduce the expected response time of a request? Do you increase the utilization of each server, randomly respond with an error, or increase the pool of servers supporting the request? You're not answering me. Where's the answers? Are you guys awake? Which is the correct answer? Increase the utilization, randomly respond with an error, or increase the pool of servers? Well, I have a very non-participative group here, and so the correct answer is to increase the pool of servers supporting the requests. That in turn drops the utilization. That in turn allows the expected response to be faster and allows you to meet your service level agreements in a properly designed system. So how can I access data and state? When a request lands into a service, it initially has no state other than what came. I'm going to need to get session state. The example for that would be a shopping cart. Or cached state. Examples are like product catalog, price list. There's many other usages, but this is a typical retail kind of framing for session state and cached data. So how can I manage scalable and reliable state? The way you typically do that is the session state is keyed by some kind of a session ID. The plumbing then manages scaling that session state and scaling it out, but you typically want to have one copy plus backups, right, for that session state. The plumbing also has to manage the durability of the state, and you get into trade-offs of, do you want to push it to disk before you allow someone to go on, or do you allow a small probability of losing the effect of their more recent work? Different systems have different requirements there. But the excellent responsiveness is super important for something deep, deep in the stack, and I have seen most systems push a 5 millisecond response time 99.9% of the time in a first-class session state manager, and that takes some serious engineering. So, but if you do this, right, if you have automatic services for session state and for the data that is being provided that is like the product catalog and price list, then your app code itself is given a different world where it can just deal with the application behavior and not think about plumbing. Just like I can go home to a condo and not think about keeping the building running. And so these applications typically build their app in two pieces. The back-end feed and data crawl processing, which we're going to talk about in a minute, and then the front-end web service, which we've talked about here, which is feeding into how do these pieces fit together. And the point is, the plumbing, the environment, the condo building should prescribe how to access the services. How can I get at my session state cache and service calls, the service calls to have one service call another, with special interfaces, but they don't tell you how they're built. And by constraining that application functionality, the plumbing itself can make your life easy as an application developer. Now finally, one of the pieces the front end may do is applying changes to the back end. So sometimes that request will actually do work and apply the changes. And the changes that you apply to the back end are sometimes synchronous and sometimes asynchronous. It is actually more typical that it's asynchronous than synchronous. Now, an example I love is the way, as a user of Amazon.com, you can see some really cool behavior. You shopped, you have a shopping cart, you push submit, and then your email goes, like a few seconds later it goes blink, and you know your work has been submitted to the back-end services at Amazon asynchronously, and it has been asynchronously but quickly, and it has been processed, the email's been sent, and you've received that acknowledgement in your email. Sometimes you will say submit, and it takes like 30 minutes before you get the email. And that's what happens when the back-end servers are behind and are just taking their time catching up. Nothing wrong with it. It's called asynchronous processing. So let's look at the back-end and decision support. So, feeds, crawling, and logging. The back-end receives data from many sources. It may go crawl the web and look for stuff that it's then using to process. It may get a data feed where a partner that wants to sell stuff with you or a partner that's working with you in some other way deliberately sends you files of data to process. It may also get data from logging the behavior of the front end. How do I make all of this work? How does it happen? And I pull all this in and I'm going to process it. Now that back end needs to apply the online work, right? So what it does is it takes the back end application and it runs it against a data set, and then actually, in this case, the front end is sending work into it and it has to process and apply it. So the purpose of this back end, what it's setting out to do, is to look at the data that it's gotten from these four sources, if you count the actual work fed directly from the front end, and create that reference data that is going to be used to drive the website moving forward. So here's some example uses of reference data. Product catalog and price list, for example, Amazon.com. Search indices for Google, Bing, other big enterprise-specific searches. Maps, insurance rates, the ICD-9 codes, which are medical diagnostic codes. All this kind of stuff gets processed and then pushed out so the front end can get at it to talk to the user. So the general model for data is the back end processing receives data from the web by feeds or by crawling. So in come the feeds. They're coming in different ways, logs, crawling, whatever. The application code on the back end munches it and makes data to have entries to serve. That data that it produces, the product catalog, the price list, the insurance quotes, the other stuff, gets pushed either on a periodic or a constant basis into some automatic pub-sub distribution mechanism. And again, that may be batch, it may be incremental, it may be batch with a fast path for super fresh updates that are being pushed out. That goes into a scalable and distributed cache, which is implemented with lots of data spread out over lots of computers. Now the web service-facing application can come and look at that data, and it sometimes sees gradual changes in it as it is feeding information out to the users that are chattering away with the software as a service application. So let's take and let's focus in on the scalable and distributed cache and talk about ways in which it can be frequently implemented. I'm going to focus in on this piece of the flow and how does that scalable and distributed cache get implemented. So one typical technique is where you partition and replicate the reference data. So here you see the columns have the same data in it. A through E is on the column on the left, F through I, K through O. Each column has got a separate collection of data that's stored in it. And you replicate it. You keep multiple machines with that data in it for two reasons. One, to handle failures, but the more dominant reason that happens is to handle lots and lots of read traffic. So you want to make sure that the more traffic you have, the more servers you have, because if the utilization of the read traffic gets too high on that server, then you won't be able to meet your service level agreement allowing visibility into these pieces of data that are being published out to support the software as a service front end. And I want to make sure you know this is just one technique. There are other techniques similar to Dynamo, for example, where you're doing an eventually consistent hash that can store read-only data, which are also very effective. So as I plumb that cache for reference data, I want it to be easy to program the backend processing for feeds and crawl. I want to have automatic data partitioning for scale of the amount of data that I'm pushing there. I want to have automatic distribution of the data as it gets pushed out. And I want to have auto replication for request scale. So the idea is this system should just adapt. You put more data in it, it partitions more. You put more traffic on it, it gets more replicas. And this is the class of concierge service that can be built for software as a service if you constrain the usage pattern. So what are the styles of backend processing? The backend input is crawling, data feeds, user and system logging, and the front-end calls. The backend output is reference data, front-end responses, analysis results, and output data feeds to others. I may be somebody who's creating a data feed to send to my partners. So there's three broad classes of implementation style. Relational database and normal app is just one form. It's just fine. Put up a database, put up an app, it's fine as long as that meets your scale. You can also do big data in a parallel batch. Think MapReduce. Think running the batch job. 2 hours later, I have the new data that I can push up into my data caches. And finally, you could have big data with event pub sub. There are emerging systems. Percolator was documented by Google, where a change comes in and it pushes its way through, and then the change comes out within seconds and minutes to be fed into this cache. Very much of this genre. So when I think of a relational database and a normal app as the implementation style, I might do a database trigger running in the database. I might do an n-tier app. I might do some other app running in VMs. I have the advantages of relational, but at some point that may not scale all the way that I want it to. So then we've seen bigger systems doing set-oriented, massively parallel batch processing. This is MapReduce and Hadoop over all of the enterprise's data. The wonderful thing about this is there's effectively no limit, and there are emerging declarative high-level languages that are easy for analysts, and you then can produce reference data or BI analytics out of it. And finally, a newer area is the event processing pub sub, where work is coming in, it's rattling around the massive data sets, making changes and processing it within seconds, right? And then sending that out to go into the data caches. And the application code processes each subscription event. And in this new world, we're seeing massively parallel transactional record updates, and I mean classic transactional. I've spent my time on that. The Percolator paper is the one that will show you that stuff as that example. In rapid processing of events to fresh reference data. So what are the concierge services for the backend? Big data, unified data access. I want to get at everything and anything my enterprise has. The relational database for silos and services. I may plug in a relational thing to do extract, transform, load to stage data into that big data store. I need to have a fault-tolerant and scalable storage. So the cloud for that backend has the cloud-managed storage for both big data and relational. I want to have automatic inside my data center and across data centers for disaster replication. Massively parallel batch and event processing, where I've got high-level set-oriented operations and incoming events call pub-sub style apps which transactionally update big data. Automatic scalable reference data caching. Multi-tenanted access control, so lots of people can get at data and you share what's appropriate to share and keep them isolated where appropriate. And then finally, prioritized SLA-driven resources for this back-end processing so I can make trade-offs that are automated. Okay, question. What is the role of the back-end portion of the software as a service application? Is it to generate reference data, to be used by the front end to display business information, to reliably process business transactions, or both?
Pat, wait for about a minute for people to respond.
Okay.
People have been responding to all the polls. It's just that the timing doesn't work out. And at regular times, you may need to refresh, and then we'll see results.
I think I've been mistaken by not refreshing. Thank you. Looks like people are getting the answer. Should we move ahead?
After some Jeopardy music, yes, move ahead.
Do, 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 do. Do, 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 do. Excellent. The answer is C, both A and B. They're both very important usages of the backend. So let's move ahead and see if we can actually keep to our time schedule, because I should be out of time right around now, but I'm not done. So multi-tenancy, making it work. Landlords, management staff, keys, and privacy. Okay, in a rented apartment, an owned condo or rented house, the landlord and engineering staff have a key because they may need to get in there for very important things, but they get into a world of trouble if they, go in for other reasons. When I rent or lease a property, I have a bi-directional trust relationship. If I am the landlord, I trust that the tenants will follow the rules, pay the rent, not trash things, and not bug the neighbors. And then but the landlord, as a landlord, I grant access to the property, which is trusting, and they trust me to keep the services going and back and forth. Now, the landlord-tenant laws and rules took years to establish, and there are even more complicated rules in condominiums where I share ownership, and different laws and expectations for different condos for housing, retail, and office, for example. So public-private sharing and trust. In a public cloud, I have multi-tenancy across companies, and that is typically at the granularity of files and VMs, but others like Salesforce actually offer finer-grained sharing of records in a database. And the cloud user has to trust the cloud provider with its confidential data. And I will tell you, one of the things that I love most about being at Salesforce is the emphasis on trust for exactly this reason. It's awesome. But the laws and conventions are being established in terms of legal worlds. It's this issue of trust at this point. Private clouds, you're running on-premise at the enterprise and sharing within the enterprise, has fewer legal challenges. It's harder for the enterprise to gain the scale advantage across enterprises. And so you can have hybrid enterprise deployments where some apps are at home in the IT shop, in your own data center, some apps are in the public cloud. But figuring out how to work that trust to the public cloud and make the enterprise application integration across those environments is a wonderful, interesting, emerging area. And so you see semi-private clouds also, where you have people who are sharing the coarse-grained allocation of computing resources like racks of servers, which leverages data center efficiencies, but has a coarser-grained sharing. All of these issues are coming about in a very interesting way. So let's conclude and get to Q&A. I want to define the constraints and empowerments. Programming platforms define APIs, and they give you a model for use and platform support, and different ones have different things. Shared buildings have different expectations for usage. And nowadays, you build a building without knowing who will occupy it, but they're built with an expectation of how they will be used. And so you're not allowed to live and sleep in a retail store or an industrial park. So as we move deeper into cloud computing, we need to define the usage expectations for platform as a service. It is okay if a particular platform as a service helps a lot of applications but doesn't help gaming, for example. It helps enterprise apps but not gaming. That's an example of different classes of applications that are supported differently. You need to support these great concierge services, but the package deal includes acceptable constraints for that. So again, front-end concierge services can be auto-scaling, auto-placement, capacity planning, resource marketplace, A/B testing, auto-caching and data distribution, and session state and management. Those very important services that we can build at the front end. The back end, big data unified data access, relational databases doing silos and services, fault tolerance and scalable storage, massively parallel batch and events, automatic scalable reference data caching, multi-tenanted access control, and prioritized SLA-driven resources. These are the class of services that we can make automatic for the back end. And I want you to remember that condos impose constraints. My brother raises pet chickens for eggs. But you know what? He lives on 3 acres. He doesn't live in a condo. And in my condo, you are not allowed pet chickens. Condo buildings are designed with an expectation of their usage. You've got a density and a lifestyle and restrictions. But in exchange, you get tons of advantages with exercise rooms, concierge wine storage, parking, lots of rooftop patios for barbecuing sometimes with grills and fireplaces. But it is those constraints that allow the community to exist. I can share the services, building maintenance, and expenses, but they're based on sharing for reduced cost and increased benefits. If those constraints are not correct for you, condo living isn't right for you. If you want to raise chickens or horses and have crickets in your backyards, then this isn't for you in that environment. But if your lifestyle fits the constraints, condo living can be great because there's no lawn to mow, no gutters to sweep, no trash to take to the street. So now we have a poll question. Do you raise pet chickens at your condominium? Come on, let's push the results. Whoop, refresh. I pushed the results. I didn't mean to do that. So nobody raises at the condominium. Okay, I'm shocked. I don't raise pet chickens at the condominium. So the next one is, does your homeowners association provide bulk discounts on chicken feed? Nope. So we'll push the results. Nobody has. Okay, I'm surprised. So what about those forces driving us to the cloud? With data center economics, in a public cloud, the cloud providers have a large and efficient data centers, fine-grained and multi-tenanted. But the thing is, you have to trust the cloud providers' sharing mechanisms in that public cloud. In a semi-private cloud, where it's a coarser-grained allocation, there's a limited amount of trust. I may have VPNs, virtual private networks, between the racks. So I'm only trusting that the physical data center guy isn't going to unplug plugs. I'm not trusting that the software will keep everything straight. So we're seeing this, how fine-grained do I share, and the finer grained I share, the more efficient it can be and the more advantages I can get, but the more I need to trust. Shared data. We are evolving towards all data shared in a big data store. And the question is, what's the granularity of that? Is it per enterprise? Is there data that's shared across enterprises where it's legal and appropriate to share it across enterprises? But having a common, distributed, uniformly addressable data store, and then I can manage that replication in a data center and across for high availability. And I can push the existing siloed databases replicated into their common store. Shared resources, coarse-grained sharing, gives me a set of advantages with VM and physical servers offering fungible units, and existing apps can run in these. And that's been the fun thing about the VM environment, is that many existing apps don't have to change. But the fine-grained environment is talking about new ways of writing apps, which then empower front-end services and make things work in a different fashion, but don't necessarily run the old code. So this is the last slide, okay? I always talk about takeaways when I try to write a presentation. So the takeaways are that shared buildings became successful by constraining and standardizing usages with apartments, condos, retail, offices. But not everybody accepts the constraints. Some buildings are built custom. A ballpark is not something you can go and get a real estate agent to acquire for you, as is a super Walmart. You have to build it. Standardization, though, allows for outsourcing and sharing of many things. And so we ended up evolving our usage patterns and expectations and laws to make it easy to pre-build buildings without knowing who was going to use it, just knowing how they were going to use it. And I'm arguing that the standardization of usage is going to empower migration of work to the shared cloud. Lower level standardization, like VMs, supports more apps but fewer services. Higher level platform as a service is it's new, it's emerging, but it can offer many advantages and many more services, but requires a change in your expectation of usage patterns. And so we have to define and constrain usage models for important types of apps, which allows enhanced sharing. And then enterprises will gain tremendously from public and or private clouds. Sharing across apps, both front and back end, can increase utilization. Fungible resources can spur efficient provisioning and allocation, and using the cloud clarifies the relationship between business apps, IT control services, and those concierge services empower IT and liberate business applications. So now, we've got time for questions, not quite as much as I wanted, but we're doing okay.
Thank you, Pat. We have lots of questions. We won't be able to answer them online, all of them. Many people are asking about security, and they are concerned how we can deal with security in this environment. Could you comment on that?
Sure. The question is, in many ways, there's a question of trust, okay? And people who are completely not willing to trust the platform as a service provider will buy their own computers and run a private cloud. Increasingly, there are emerging providers, Google App Engine is one, Salesforce is another, that are giving the ability to talk about these services flowing in and out and not messing up and making sure that the data is kept isolated at a finer grain. And so there is no magic answer. And some classes of data are still going to get a lot of very paranoid constraints, as they should. But it's simply a matter of what is the trusted computing base and how do you interact with that trusted computing base.
All right.
Yep.
Another question. How can multi-tenancy be used for customization? Can this be part of the engineering work for the cloud, or should it be kept as an application concern?
You most certainly can build customization into a multi-tenant environment, and it's something that Salesforce has provided. Salesforce runs on top of Oracle databases, and there's a wonderful paper that was written 4 or 5 years ago for SIGMOD about this, and has interpreted schema. And so you can extend columns and so forth, and the way they do that, the way the company does that is by having a bunch of hundreds of pre-allocated numbered columns in Oracle, which are then dynamically bound to a particular customer as they access their records, which have different keys. And so that's one example at a DDL level. Absolutely, customization can be done, but it just requires thoughtful and clever new techniques that allow you to basically interpret it on demand as you support the individual tenant.
All right. When you talked about composite request services and deep trees and so on, how do you handle if a service is not available? I mean, even with redundancy, some things always fail.
Well, and it depends. I understand. So if you watch Amazon.com, in the Dynamo paper in 2007, Amazon quoted that there were over 150 service calls per HTML user screen refresh. And if you go and just get onto Amazon and just shop, and you watch closely, different pieces of the screen are filled in at different rates. And so you will see the recommendations are coming after the reviews and the information about the product, and it all kind of pieces together, boom, 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 and sometimes in different orders based upon whether what the services inside of the Amazon data center are doing. And in many cases for that, there are sheddable responses. Some of the answers that come back, you're okay if you miss a review. You're okay if you miss some of the customers who bought this typically bought that. And so that's one answer that can occur. It just depends upon how one builds the app. But in that case, there's a conscious effort that the top-level indication of the services will accept some ORing of things that it's okay to not get an answer for, as opposed to the intersection of the probabilities of everything coming back. And so the question is very clear, I understand. The more things you have, if every one of them has to answer, the more you run the risk of things being slow and or unavailable. So the common sense makes sense.
Good. Do you have any comments on private clouds integrating with legacy non-cloud application regarding access control?
Well, we're all struggling as an industry with, what's identity and what's access control and how does it work, because there's all these disparate systems that have different notions of who's who. And so at some level, there's no magic here. You simply have to map one identity system into another and then talk about the access control that goes with the various identities. In my mind, we're going to see a ton of existing systems surrounded. you won't throw them out. They'll be there, but you'll have some front-end piece of hardware that can talk one identity to its right side and a different identity to its left side and figure out how to map that. And I think that that's going to be part of the evolution as time goes on, because we simply have to bring all of these pieces together, both the implementations of the systems, but also, as was mentioned here, the identity and authorization.
All right. How do you see someone balancing, giving an SAS, balancing the money cost and the response time of the cloud? Is it something that an application developer should be thinking of, or should be the cloud balancing it out, or what?
Well, I think in my mind what's ideal is that the response time and the cost to implement that response time should be coming from the magic of the concierge services of the platform. I am not telling you that it's automatically there. I'm not. This is something that there's no good reason we can't build. There's no good reason we can't create platform environments that offer this. But it should be one of those things where, hey, you want this response time, it's going to cost you this much. You want it this response time, it's going to cost you that much. We haven't built that yet. We should.
What do you suggest are the fundamental re-engineering of business or consumer applications architecture or functional organization that increase the application value as well as the management of the applications?
Well, I mean, one of the areas that I think is going to become increasingly important is there's all of these silos in most enterprises. And to be able to create an environment that surrounds the enterprise and arguably surrounds the customers and the employees, where the customers and the employees interact with something that is a lot more uniform and gives them offline ability and things of that nature. But then in the back end, the workflow that involves the user will talk to the older enterprise applications. I think this is emerging, and I think that will offer us a great deal more consistency as time goes on. I can't tell you how many times my wife has just said, I changed the address with the bank. Why don't they know our new address? As it's difficult to propagate that knowledge through it. And these are the kinds of things that we'll see. This is not necessarily a cloud-related answer. It's more of a, how am I tying all this stuff together? But increasingly, these new applications are going to be run in a cloud, public or private.
Sure. And one kind of open-ended question. What typical cloud concierge services do you see in the future? And we'll wrap this with that question.
Well, I think I just really pounded a bunch of them, right? I think the ones I'm talking about here are some present and some not. Most of them are stretching what is available. But honestly, much of what I was talking about here is predicated on an assumption that there is a standard platform as a service. This pattern that I have seen here, I've seen it with variation in a number of different companies, but it's not regular. It's not where we've emerged and said, okay, here are the APIs. You do it this way, and now I can invest a lot in these concierge services. And that's why I say that the platform as a service world is emerging, right? But this is no big surprise. For years, almost the definition of a platform is something that has been done over and over and over in many different applications, and then someone comes along and says, I'm going to do it in a standardized way, and it won't run for those previously existing applications, but the new application that wants to do something similar can just take advantage of this simple way of doing it. And that is where I think we're not there yet, and I think we need to get there.
Perfect answer. Well, we have run out of time today. This webinar will be available on demand at learning.acm.org/webinar/condos. And don't forget to check out ACM's other learning resources in the area of cloud computing, software as a service, management of data, and beyond. In closing, I'd like to once again thank Pat Helland for his informative and exciting presentation, insightful answers to many questions. And a special thanks to our audience for taking the time to attend and participate today. Please take a moment to fill out our brief survey, which should only take 2 or 3 minutes to help us improve your next webinar experience. Please check acm.org and learning.acm.org in the coming weeks for announcements on upcoming webinars. This is Yannis Ioannidis saying hope you can join us next time. And if you have any ideas for future topics or speakers, please email them to learning@acm.org. Thank you very much.
Thank you, Yannis. Thank you, Jan.
Thank you all.